Hello, we'll now start summary question 7.3 from the Nelson Thornes textbook, and these questions are all about moments. Question 1. A child of weight 200 newtons sits on a seesaw at a distance of 1.2 metres from the pivot at the centre. The seesaw is balanced by a second child sitting at a distance of 0.8 metres from the centre. Calculate the weight of the second child. So, as far as moments go, this is a very simple question. We can draw our seesaw on. We've got some kind of pivot point here. We have a weight this side and a weight this side. So we've got one child here of 200 newtons, and he's sitting at a distance of 1.2 meters. And then we have a second child sitting at 0.8 meters, and their weight we don't know. Always drawing a diagram out. We've got a diagram now. We can now say that the anti-clockwise moments will be equal to the clockwise moments. So let's look at the clockwise moments first. Well, that's going to be the weight trying to turn it in this direction, which is the unknown. So we get force times distance for moments, so we get W times 0.8 will be equal to the anti-clockwise moments. Well, that's going to be this one, which would be 200 times 1.2. So this follows the convention W1 D1 is equal to W2 D2. So the clockwise equals to the anti-clockwise. So to get W, we've got to divide by 0.8, so we get this bit divided by 0.8. Which is going to equal 300 newtons. And that's the answer to question 1. Question 2. A meter rule pivoted at its centre of mass supports a 3 Newton weight at its 5 centimetre mark, a 2 Newton weight at its 25 centimetre mark, and a weight W at its 80 centimetre mark. Sketch a diagram to represent the situation for A, and for B, calculate weight W. So again, we're going to draw ourselves a diagram out. The tricky part about this one is that they're giving you the values as they are from 0 on the meter rule, rather than giving you the values from the fulcrum. So we have to make that adjustment, because we only work with values from where we take moments around, and in these simple questions we'll always take them around the fulcrum. So what I would do in this situation is make that change as I read from the question to my diagram, so that the numbers on my diagram are correct for my maths. Okay, so the first thing is it's pivoted at its centre of mass. It's a meter rule, so it's 1 metre long, pivoted at its centre of mass, and we assume it to be a uniformly distributed mass, and therefore the centre of mass of a meter rule that we'll always take will be at 50 centimetres. Okay, so there's our fulcrum there. It supports a 3 Newton weight at its 5 centimetre mark. So its 5 centimetre mark will be 5 in from this way, but we want the distance from here to here. So let's put we've got a weight there. How high is it? It's 30 newtons, and between there and there there'll be 50, take away the 5 will be 0.45. I'm not sure if that's going to be quite big enough for the screen, but we'll put the numbers bigger when we put them here. The next mass we have to add on is a 2 Newton weight at its 25 centimetre mark. So 25 centimetres is going to be about there, so I'll put a dotted line on the top so I can use that, and then add the weight here. and this one is 2 newtons, and the distance from the centre to that, well, that's easier, that's 25 centimetres, so 0.25. So that's the 2 that I've given there, and then I need to add a weight at its 80 centimetre mark, so we're now on the other side of the fulcrum, 30 centimetres from the fulcrum, we have a weight W and 0.3. So by redrawing it out correctly to the way I want the numbers, we can now quickly transfer them straight into our calculations here. In this situation, we've got one clockwise force, so we've got our W1 D1 part, which is going to work out to be W times 0.3. So that's our one clockwise section. But we've got two anti-clockwise sections. When we get that situation, we're going to do it mathematically like this. We're going to take the moment of this one and add to the moment of the second one. And we could just add subsequent moments if we needed to. So let's take W2 to be this one nearest the fulcrum. So that will give us 2 times 0.25 plus this one 3 times 0.45. That is going to work out at, if we do a little bit of calculations, we can times 2 times 0.25, it's going to give us 0.5. 3 times 0.45 is going to give us 1.35, and this is going to be 0.3 W. To get that to there, we've got to divide, so then we get that W be equal to 0.5 plus 1.35 divided by 0.3, and I believe the answer works out to be 6.2 newtons. Question 3. In Q2, the 3 Newton weight and the 2 Newton weight were swapped. Sketch the new arrangement and work out the new distance of the weight W from the pivot. So what we're doing this time is we're fixing W at 6.2. We're going to move it to counteract the fact that we're going to swap these two weights round. Let's redraw it out. We've got our meter rule, pivot at 50 centimetres. We've got a mass here, this time of 2 newtons, and a mass here of 3 newtons. We've got our centre point here, we've got a weight here of 6.2 newtons. What we don't know this time is the distance on that side, so we'll call that distance X, and these stay the same at 0.45 and 0.25. So we can use exactly the same as before. Clockwise now, where instead of W times 0.3 we have 6.2 times X. So just swapped them around. We know W is 6.2. And then the other side, well, we're going to do this, but we're going to do it the other way around. So we're going to have 3 times 0.25 plus 2 times 0.45. So we're going to end up with 6.2x is equal to 0.75 plus 0.90, and therefore x is equal to 0.75 plus 0.90 over 6.2, which gives us an answer of 0.27 metres. So it'll be positioned at 27. Oh, I'm slightly off the screen there. 27 metres. Okay. Question 4. A uniform meter rule supports a 4.5 Newton weight at its 100 millimetre mark. So that's 10 centimetres or 0.1 metres. The rule is balanced horizontally on a horizontal knife edge at its 340mm mark. Sketch the arrangement and calculate the weight of the rule. So this is the sort of one mass and the mass of the rule situation that you're going to get a lot. So when I do these, I tend to draw the rule with thickness, so I can imagine that I'm calculating including the mass of the rule. It's pivoted at 340mm or 0.34 meters, so that's somewhere around there. And I can mark it in for myself if I want to. 0.34. And it's going to have a mass on this side here at about 10 centimeters, and we can mark that distance to the fulcrum above. If this was 0.34 and this is 10 centimeters in, this must be 0.24 meters, and that mass is 3 newtons. Then the weight this side is balancing the mass this side. Where do we take the weight to act from? Well, again, we consider it to be evenly distributed mass, in which case the centre of mass will be at 50 centimeters. And the convention we use is when we talk about the weight, we call it W0, and the weight of the ruler. So at 50 centimeters, this distance is going to be, well, this is at 0.34 meters, so this is going to be 0.16 meters. Hope that's clear on the video. And it's the same simple scenario again. We're going to do the sum of the clockwise against the sum of the anti-clockwise. So clockwise is the weight of the ruler. Kind of turn it that way, which is W0 times 0.16. And that will be equal to the mass trying to turn it the other way, which will be 3 times 0.24. So therefore 0.16W is equal to 3 times 0.24, which would be 0.73. And then when we made a slight mistake, just noticed that. This is actually 4.5 newtons, where I don't really want to notice that before I did. So we'll just make a corrections here. 4.5. So 4.5 times 0.24, I think is 1.08, and then carry that over. W is equal to 1.08 divided by 0.16, which is equal to 6.75 newtons. And that's the answer to all the questions from section 7.3.